Super Bowl halftime 2012. Beyoncé hits the stage. Twitter sees 268,000 tweets per minute. The timeline system collapses completely. On-call engineers wake up to pagers firing across the entire fleet. The naive database approach couldn't survive a single viral moment, and Twitter had 238 million daily users depending on it. This wasn't a corner case. It was the fundamental flaw in how social feeds get built. The fix required rethinking every assumption about when to compute a timeline, at write time or at read time. Twitter processes 6,000 tweets per second at peak load. That's 500 million tweets every single day. Those tweets must reach 238 million daily active users, each with a personalized ranked feed in under 800 milliseconds. Now think about the math. The average Twitter user follows roughly 400 accounts. Loading a timeline naively means 400 separate database queries, merged sorted by timestamp. At 238 million DAUs loading timelines multiple times per day, that's 100 billion database queries daily. At 100 milliseconds per query, that's 10 billion seconds of compute. Physically impossible. Something has to change. Think of it like a newspaper printing press. The press runs once and delivers papers to every doorstep. Not every reader printing their own copy on demand. Twitter's push model works the same way. When you tweet, a Fanout worker immediately writes your tweet ID into every follower's pre-built timeline cache in Redis. No follower ever queries the database at read time. Their timeline is already assembled and waiting. For a user with 100 followers, that's 100 Redis writes, microseconds each. Timeline reads become a single read-as range call. Milliseconds become microseconds. This is Fanout on write. But here's the catch. It breaks completely for celebrities. Here's exactly what happens when you tweet. Step 1. Your client sends the tweet to the tweet ingestion service. It validates content, extracts media, resolves URLs, and assigns a 64-bit Snowflake ID, all in under 200 milliseconds. Step 2. The tweet gets written synchronously to Manhattan, Twitter's custom distributed key-value store. Step 3. A Kafka message triggers the async Fanout worker. Step 4. The Fanout worker reads your follower list from FlockDB, Twitter's social graph store. Step 5. The worker calls ZADD on each follower's Redis timeline key, inserting your Snowflake ID as both member and score. The follower's timeline is now updated before they even open the app. Katy Perry has 108 million followers. Pure push means one tweet triggers 108 million Redis ZADD operations. That's not a background task. It's a write storm that blocks tweet delivery for minutes and saturates your Redis cluster. Twitter's solution is a hybrid Fanout threshold set at roughly 10,000 to 20,000 followers. Regular users below that threshold get pure push. Tweets land in follower caches immediately. Celebrity accounts above the threshold get no push at all. Their tweets stay in Manhattan only. At read time, the timeline service detects which celebrities you follow, fetches their last 800 tweets via direct Redis lookups, and merges the results with your pre-built cache. Now here's where it gets interesting. How does Redis actually store these timelines? Twitter stores every user's timeline as a Redis sorted set, called a Z set. The key is timeline:user ID. Each member is a 64-bit Snowflake tweet ID. The score is the timestamp used for ordering. Max size is capped at 800 entries per user. Why 800? Twitter's ranking model needs a candidate pool of roughly 800 tweets to select the best 50 for your feed. Fewer candidates degrades ranking quality. More wastes memory. Each entry is 8 bytes, a Snowflake ID. That's 6.4 kilobytes per user timeline. At 238 million daily active users with hot timelines in memory, the total Redis footprint is 1.5 terabytes of active timeline data. Twitter runs this across a sharded Redis cluster, not a single instance. This is why engineers lose sleep when a shard goes down. Here's a production-style Python implementation of the hybrid timeline assembly. The function fetches the user's pre-built Redis timeline, the fast path for regular accounts. Then it identifies which accounts the user follows that exceed the 10,000 follower threshold, the celebrity list. For each celebrity, it performs a direct Redis zRev range lookup, fetching their last 800 tweets. It merges those results with the pre-built cache, deduplicates by tweet ID, and sorts the combined set by score descending. The result is a unified candidate pool of up to 800 tweets ready for ML ranking. Notice the celebrity lookup is just n Redis calls, not n million cache writes. Following 50 celebrities costs 50 lookups, not 500 million Fanout operations. Every tweet has a 64-bit Snowflake ID. The structure is precise. 41 bits encode milliseconds since a custom epoch, 10 bits encode the machine and data center ID, and 12 bits encode a per millisecond sequence counter. This means higher ID always equals newer tweet. No secondary timestamp index needed, no central coordinator, no single point of failure. Each of Twitter's tweet storage machines generates IDs independently. With 12 sequence bits, one machine produces 4,096 unique IDs per millisecond. Across 1,000 storage machines, that's 4 billion unique IDs per second. The Redis ZSet uses the Snowflake ID as both member and score proxy. ZRevRange by score returns tweets newest first with 0 additional sorting. LinkedIn, Discord, Instagram, and Uber all adopted Snowflake variants. It became the industry standard for distributed ID generation. Here's the full production stack. The client layer is iOS, Android, and web. Requests hit a load balancer, then the tweet ingestion service for writes or the timeline service for reads. The ingestion service writes synchronously to Manhattan, Twitter's custom LSM tree key value store, and fires an async Kafka event. The Fanout layer consumes Kafka events, reads the FlockDB social graph, and writes to Redis timeline shards. The timeline service reads from Redis, performs celebrity injection, then passes 800 candidates to the ML ranking pipeline running on GPU-backed inference servers. Tweet content hydration hits a mem-cached L1 cache first, then Manhattan read replicas. 3 data centers receive simultaneous writes for Manhattan. Any data center can serve reads with eventual consistency, while tweet creation requires strong consistency. Chronological timelines were Twitter's original model. Ranked timelines shipped in 2016 and became the default in 2019. The pipeline runs in 2 stages. Stage 1, candidate generation. The timeline service fetches 800 candidates, your pre-built Redis cache plus celebrity injections. Stage 2, scoring. Twitter's heavy ranker, a 48 million parameter neural network, scores each candidate on predicted engagement probability. Features include the author's historical engagement rate with you, tweet freshness via exponential decay, media presence, tweets with images or video rank roughly 30% higher, and social proof from your network. Twitter open-sourced this algorithm in April 2023. Serving latency target is under 150 milliseconds per timeline request. CPU inference at 238 million DAUs would require 10 times more hardware than GPUs. This is why the ranking runs on GPU-backed inference servers. Let's put the 2 models side by side with real numbers. The naive pull approach, read-time fan-in, forces 400 database queries per timeline load. At 238 million DAUs, that's 100 billion queries per day. A Justin Bieber tweet to 100 million followers triggers a thundering herd, 100 million simultaneous reads on one database row. Ranking on demand requires fresh ML scoring for every single page load. Now the push approach. A tweet is written once to Manhattan. Fanout distributes it to follower caches asynchronously. Timeline reads are a single Redis range, sub-millisecond. The celebrity problem is solved with hybrid delivery, at most 50 extra Redis lookups per read. The heavy ranker pre-scores candidates in under 150 milliseconds on GPU. The difference isn't marginal. It's the difference between a working product and a crashed system. Here's the Fanout worker pattern that enforces the celebrity threshold in production. The worker consumes a Kafka event containing the tweet ID, author ID, timestamp, and author follower count. If the author has fewer than 10,000 followers, the worker fetches the full follower list from FlockDB and pipelines Redis ZADD commands in batches of 500, using a Redis pipeline to minimize round trips. After insertion, it trims each timeline to 800 entries. If the author exceeds the celebrity threshold, the worker only writes to the author's own tweet list, not to any follower's timeline cache. That single conditional saves billions of Redis writes daily. Notice the pipeline batching. At 108 million followers, even individual ZADD calls at 1 millisecond each would take 108,000 seconds without batching. Instagram's feed is architecturally identical to Twitter's, but with extra complexity. The average Instagram user follows 500 accounts, denser than Twitter. Instagram uses Cassandra for activity storage, likes, comments, follows, and a custom feed aggregation service. Photos and videos require separate CDN assets fetched in parallel. LinkedIn's feed must handle professional signals, endorsements, job changes, article engagement, layered on top of the same Fanout infrastructure. Discord adopted Twitter's Snowflake ID format verbatim for message IDs. At 4 billion messages per day across 19 million active servers, Discord needed time-sortable distributed IDs without a central coordinator. TikTok's For You page inverts the model entirely. It's not social graph-based Fanout, but item-based collaborative filtering at 1 billion daily active users. Same Redis ZADD primitives, radically different ranking signals. Twitter's timeline teaches one unforgettable lesson. Compute at write time when reads outnumber writes. Fanout on write, Redis ZSets, hybrid celebrity delivery, Snowflake IDs, and GPU-backed ranking. Each piece solves one specific failure mode at scale. Next up, how Discord stores 4 billion messages per day using Cassandra, and why they migrated away from MongoDB at 100 million messages. Subscribe so you don't miss it.